Welcome everyone to the wonderful world of calculus. In this video I kind of want to go over the motivation behind what we are doing really for the first half of this class, but in particular for chapter 1. So the first big topic in calculus is slope. Right? This is an extremely important topic not just for math but across all of the sciences, and to motivate this I want to give you this example. Right? So suppose we're driving from Lansing to Detroit. And to the right, I've given us a graph, right? No equation or anything like this for the function, but just the graph representing your distance from Lansing. So you can see here at time equals 0, you kind of start off in Lansing, right? Your distance is 0 away. And then over here, about 60 minutes later, our distance from Lansing is a bit over 70 miles away, right? So this is miles, this is minutes. And so the question is, what is your average velocity on the interval from 10 to 40, right? So this is going to be 10 minutes to 40 minutes. This interval right here is given us in the independent variable, right? So this is time in this case, time in minutes. And you can see actually I've given us these points. So at time 10 minutes, it looks like we are only 4 miles away from Lansing. At time 40 minutes, it looks like we are 56 miles away from Lansing. And again, the question is, what is our average velocity? And the claim is this question right here can be solved using slope, right? So we would ask ourselves, well, if I want to do the average velocity, it would be, well, how far did I travel? So I'll just denote this, how far, divided by, right, how long it took. I'll just denote this, how long. Well, you can see that we started off here 4 miles away from Lansing, and we ended up 56 miles away from Lansing. So this is going to be 56 minus 4, that's going to be 52. Now, how long did it take? Well, we started off 10 minutes here, that's when we were 4 miles away, and we ended, again, at 40 minutes. So 40 minus 10, or you could just think, right, what is the difference? If I started here at 10 and I ended at 40, well, it had to take 30 minutes. So in this case, on this interval from 10 to 40, our average velocity was 52 miles for every 30 minutes. Or another way that we'd probably say this, right, if I multiplied by 2 on top and bottom, this would be 104 miles per, well, 60 minutes is 1 hour. So 104 miles per hour. Now that is really fast. I'm certainly not advocating, going on average 104 miles per hour. But this is the average velocity, right, of at least this graph, right? So hopefully yours is a bit slower when you're traveling from Lansing to Detroit. All right, so we see here, again, that this is somehow related to slope, right? In this case, we wanted to know how far. So this case, it was this distance right here. So that is the 56 minus the 4. That's the 52 miles. That's the height. And then how long, that's the run here, right? So this is now moving over 30 minutes. So you can see 10, 20, 30 minutes. So the slope idea, rise over run, actually gave us the average velocity. Now, I'd like to ask a follow-up question that's sort of related to this and kind of push us in the direction that we're going to be going for a lot of calculus, actually. And the question is, at what time is your speed the greatest? Right? Because you can see that this isn't just a straight line from these 2 points, right? We kind of have some curvature going on here. And so the question is, at what time is your speed the greatest? So I'm going to give you a minute. Go ahead, please pause the video and try to answer this question. Try to reason out at what time is your speed the greatest, and then I'll go ahead and explain it. So again, pause the video now, then I'll spoil the surprise. All right, here we go. And again, the question is, what time is your speed the greatest? And we saw that really our speed, or our velocity in this case, was given by slope. So really the question of when is your speed the greatest, this is equivalent to when is your slope the greatest. And so you can see kind of, maybe if I looked at around between minutes 10 and 11, right? If I went ahead and maybe drew an extra point right here, and between minutes 10 and 11, we can see this is maybe our slope. And so it's positive, right? We're moving in this positive direction. However, maybe that's not as big as at 20, right? So if I took between 20 and 21 or something like this is my best approximation, right? And if I was to draw the slope between these 2 points, maybe I'll do it, we'll say in orange. So we'd say that the slope here is even bigger than the slope back here, right? It looks steeper. We have more rise for the amount of run that we did. Okay, and so given that, when I kind of stare at this and I kind of think about these kind of close consecutive points to some extent, and I'm trying to figure out where is my slope the biggest, well, again, we have to estimate here, right? We don't have the equation, so maybe we can't get a unique correct answer, but staring at this graph, I would say probably between around time 25, between minutes 25 and 26, the slope seems pretty big. But really, anywhere between 20 and 30, the slope seems, pretty big. But I'd say, especially here at minute 25-ish, it's especially large. And then you can see after that, maybe if I go over here to 30 or so, we can see between minute 30 and 31, it starts to shallow out. Over here, minutes 35 to 36, it starts shallowing out even more. Here at minute 40, it starts shallowing out even more. So I would say around minute 25. Again, this is an approximation, but around minute 25, our slope, and therefore our speed, is the greatest. Okay, so we see that actually slope gives us something useful. And the claim is that it gives us a lot more than just velocity, right? It'll give us, in general, for these average rate of change problems, which is really what I did here, it's not just for velocity, but it's for so much else, right? We are very interested about how quantities are changing. So for instance, stock values. Is the stock increasing or decreasing in value? Infection rate, right, for disease. Is that going up or is that going down? Chemical reactions, if you're in chemistry, population growth in biology, the rate of change of velocity itself, right? How is velocity changing? That's going to give you something about acceleration. Change, right? Rate of change for monthly sales. How much are your sales? Are they going up? Are they going down? What's happening? And temperature changes. Again, all of these things can be answered by talking about the average rate of change, right? How quantities change is a very interesting subject. And so we want to be able to dive into that a little bit more than we've been able to in the past by using calculus. So that is kind of the first half of calculus. In fact, in all reality, in chapter 1, we're going to get a little bit distracted, right? So we're going to get distracted by this idea that you saw I just kind of took 2 consecutive points, 2 points that were very close together. It turns out in order to have a rate of change at a very specific point, we don't have right now the mathematical skills to be able to do this. So in fact, chapter 1, we're going to be talking about limits. The idea is how to get these points very, very close together in order to be able to talk about the slope, in this case, which represented speed, at a particular instant in time. So that's what chapter 1 is going to be about. It's kind of a small diversion. We'll do a little bit in 1.4, motivating more this average rate of change stuff, but then we're going to be thinking about a topic called limits. And that's what we're going to be doing for the rest of chapter 1, talking about limits so that we can get these points quite close together so we can actually talk about how something is changing at a particular instant in time. And that is chapter 1. All right, go ahead, get started in your 1.4 video. I'll see you then.